Okay, so this is the question that we left off in the last class and the last video. This is a product rule question. And on the test, especially when it relates to chain rule, we might be more specific than last time. In this case, like telling you to use the product rule or use the quotient rule, but you're also going to have to incorporate the chain rule. This is our multi-step equation. And actually, for fun, in another module, I'm going to show you some examples about how these chain rule or derivatives are used in physics and science questions, problems that are a bit more complicated that we're not going to visit in this course, but just to give you some kind of exposure to what you might encounter in first year university, right? So derivatives is, and the chain rule especially, very important concept for the future. Just gonna get rid of my meeting controlled. Okay. So here is the question that we're gonna start off with today. So another product rule question, but we have powers. Feel free to take notes because it's a good way of working through it, even though I will be posting, of course. Sometimes by doing, you actually learn more than just by observing. Okay, so I'm going to start with f prime of x because I am differentiating. I'm solving for the derivative. And I'm going to start with taking the derivative of the first function. So I'm going to bring the 3 down. I'm going to keep my x plus 4 to the power of 3. But I'm going to make sure to subtract 1 from that power. Now I have to remember now, this is the outside of the function. I have to multiply that by the derivative of the inside of the function. That's going to be, the derivative of x plus 4 is going to be 1. So this is using the chain rule to figure out what the derivative of my first function is. Okay, so if this is my g of x, for example, this is going to be g prime of x. Now, the product rule says we take the derivative of the first function and we have to multiply it by my original second function. So if my second function is x minus 3 to the power of 6, I'm going to call this my h of x, then I have to multiply all of this times h of x minus 3 to the power of 6. That's the first part of the product rule. Now I have to take the derivative of h prime of x. I'm just going to continue on a separate line here. Remember that this is a sum, not a difference, so I use the addition sign. Now I'm going to bring down the 6 in front. I'm going to write the rest of the function the way it is, x minus 3 to the power of 6. And I'm going to subtract 1 from that. Now I have to remember to multiply all of this by the derivative of the inside. What I've done so far is only the derivative of the outside of h of x. So the derivative of the inside would mean multiplying it by 1. And I have to multiply all of that by my original g of x, which is x plus 4 to the power of 3. Okay, now the trick to all of this is to try to separate what is in common, your greatest common factor, from everything else. But before I do that, I want to get rid of these little powers over here. So I'm going to rewrite the question as 3 times x plus 4 to the power of 2 times 1 times x minus 3 to the power of 6. Notice I've eliminated the 1 because anything times 1 is just 1, plus 6 times x minus 3 to the power of 5 times x plus 4 to the power of 3. Now notice on the left hand side of the addition side and in the right hand side of the addition side, I do have x plus 4. Oops. In there. Let's try again. I have x plus 4. Oh, don't want to do that. Undo that. There we go. So I have x plus 4 to the power of 2. And I have a common, and then I have x plus 4 to the power of 3. The greatest common factor is always the term with the lowest exponent. So even though I have x minus 3 to the power of 6, x minus 3 to the power of 5 has a smaller exponent. And then I'm also going to look at the positive 3 and the positive 6 to determine the greatest common factor. So in red, I am going to write down my greatest common factor next. So 3 and 6 have a 3 in common. I have x plus 4 to the power of 2 has the lowest exponent, and x minus 3 to the power of 5 has the lowest exponent. Now in green, I'm going to write kind of the leftovers, what I like to call the leftovers, in the brackets after I take the greatest common factor out. This is a more complicated grade, like the same concept we did in grade 9, but just much more complicated. So we're left with, if I'm considering the left-hand side, all I'm left with is x minus 3. And if I divide the right-hand side of the addition side by my greatest common factor, I'm left with 3 times 2 is 6, and I need an extra x plus 4. Now, this is going to make sense later on because, or actually in the last video, we had questions where it would say, tell me where the derivative is horizontal, right? And so remember, the derivative is the slope. So where the slope is horizontal, that's why we would set the whole equation equal to 0. And function students, how we used to tear apart the factored form of a polynomial equation to figure out the roots and all the characteristics. Even the students who are taking functions right now would have had lots of practice doing that over the last couple of weeks. This is similar to that. And this is how module 2 steps into module 3, because in module 3, factoring, breaking down greatest common factor helps us leads us to the roots of the equation, important points on the graph, which we will use for module 3 curve sketching. But we're not there yet. We're just using the derivative to simplify this. So I have my greatest common factor. And to simplify what's in this bracket, I would simply get 3x plus 1, right? And you have to use your judgment when you want to show all your steps or skip right to here. When Mr. Bullock and I are marking, we're thinking, is that a logical progression, or there's no way you can just do that in your head? Don't put all your work on your scrap paper. Include as many steps as possible on the test, right? Something like this is a simple calculation, so it makes sense to go to 3x plus 5. But, you know, to be safe, I could have included one more step there. I'm, for the sake of time, simplifying a little bit in lessons. Now, if the question, like in our last lesson, said, where is this graph for the slope horizontal or the tangent line horizontal, I would set this equal to 0, take all the x values, right, solve for x, and plug it back into the original function to find the corresponding y points on the original curve, just like I did last time. So that's how we can take a simple derivative question to an application problem, right? And we are at this point in the course going to look at a lot of application problems leading up to module 4, which is going to be a unit full of words, just word problems, optimization. Okay, let's do an example where we have the quotient rule in combination with the chain rule, the quotient rule in combination. So in this particular case, the outside function, so if I wanted to let, for example, if I wanted to state let u be equal to x squared minus 3 over x squared plus 2, right? And then the outside function would be y is equal to u to the power of 4, right? Those would be the two scenarios where I would have, where did it go? The outside function and the inside function. And we could say dy over dx and what we did yesterday, the Leibniz notation, or not, right? Usually in a traditional calculus course, I want to be clear that I'm a real stickler for the proper notation. And that's why I'm not using it so much on my test, because that's something in a traditional calculus course where we take off marks when you don't use the proper notation. Here I'm teaching you guys to go straight into the equations because it's just something that you don't have to deal with in this shortened version of the calculus course. Mr. Bullock and I discussed, and the notation is not going to be so important to us this year because it does take time to teach and understand the notation, and we understand that it's a little bit more crunched, right? So usually I would say write dy over dx and du over dx and do all the Leibniz notation. Here we're going to go straight into the working with the equations. Okay, so then my y prime, right, because we're starting with y. So my y prime, I'm going to take the derivative of u first, u to the power of 4. So I would take the 4 in front. I'm going to write my original function the way it is, x squared minus 3 over x squared plus 3 to the power of 4 minus 1. Okay, that is taking the derivative of the outside. But now I have to take the derivative of the inside. And taking the derivative of the inside means simplifying this function over here. Taking the derivative of the inside means simplifying this function. Okay, obviously that's going to be a little bit more complicated. I'm going to take it step by step. So first of all, I'm going to put big square brackets because the derivative of the outside has to be multiplied by the derivative of the inside. So it's always the derivative of the top times the original, the derivative, did I start with x squared? I made a mistake when I copied this down. This should be x squared plus 3 and x minus 3 on top. So the derivative of the top would be 2x. I'm going to multiply that by the original derivative, and not the original function in the denominator. So the original function on the bottom, how I remember that is d top times bottom minus, this is not a sum, this is a difference, d bottom, so that's the derivative of the bottom, which is 2x, multiplied by the original function on top, x squared minus 3, all over the bottom squared. I have to remember to close off my bracket. So see, we can never have just moved on to chain rule if you didn't have a test where you really studied and prepared for product rule, quotient rule, and power rule, right? You need to know those inside and out to move forward in the course. The same reason why the next couple of modules, you know, I always said module 1, that's something we have to teach you, but don't worry if you did well or didn't do well. But module 2, module 3, all those concepts, we're taking the skills, just like we've taken our MCR skills to apply to this course. We're taking the derivative skills, we're applying it to graphs and curve sketching. We're taking the derivative skills, we're going to apply it to word problems and optimization. And the very last module doesn't have any of those things. So it's really important to know what you're doing here. Okay, so now I'm going to start combining everything together. First of all, let's just change this as a next step. I just want to change, oops. Try that again. I'm going to change this to a power of 3. That would be my next step, would write everything as a power of 3. I'm just trying to save some time here. And now I'm going to write y prime is equal to, I want to keep everything in the denominator. So I'm going to write a big line here. I notice that this is in the denominator, but it's to the power of 3, and this is in the denominator. So I'm not just writing x squared plus 3 by itself. I'm keeping in mind that the x squared plus 3 is to the power of 3. And then I have this x squared plus 3 on this side, that's to the power of 2. Okay, now I'm going to write everything in my numerator. So I have 4. I have x squared minus 3 to the power of 3. I have this 2x over here. I have 2x times. Now notice I can simplify this. I have a 2x and a 2x. So you can actually take 2x out as the greatest common factor. And inside of the square brackets, if I'm taking 2x out as the greatest common factor, and I've already taken my denominator out, I'm going to be left with x squared minus 3 minus x squared minus 3, which is great. That turns into 0. So having a strong knowledge of the greatest common factor can really help you simplify your questions even better. And now I just want to really reinforce, this is a 2x, not a 2 times. Please don't use the multiplication sign ever in any type of equation in grade 12 mathematics, because that can easily be confused as an x. So please, your grade 9 teacher should have told you that a long time ago, but stay away from multiplication signs. We leave those behind when we leave elementary school. Okay, so y prime is equal to, I'm going to simplify by looking at things that are in common. So 4 times 2x is 8x. What else am I missing? I know that this x squared can eliminate with this, but I made a mistake before. X squared minus 3 minus x squared minus 3 is not actually 0. When you apply the distributive property, you'll see that this was actually my copy mistake. That was x squared plus 3 minus x squared minus 3. So positive 3 minus negative 3 does give us positive 6. And I also have this x squared minus 3 to the power of 3 that I have to deal with as well. Now, going back to MCR, like I love to do, when you have terms that are the same with power, so x squared plus 3 would be a common base, I would add my exponents, so I'm left with x squared plus 3 to the power of 5. Okay, what is left to do? Well, the 8x can be combined with the 6. 8x times 6 would give me 48x. Notice, something I saw on the test, the students were quick to, oh, x squared minus 3 and an x squared minus 3, I'm going to cancel, but you have to be careful. It's x squared minus 3 to the power of 3, x squared plus 3 to the power of 5. Those are different. Therefore, those cannot be canceled out. They are not the same base. So I'm going to have x squared minus 3 to the power of 3. That is in my numerator. That's going to stay there. X squared plus 3 to the power of 5. That is in my denominator. That's going to stay there. And that's my final answer. Remember, even if you don't get the answer completely right, I'm giving you steps for your process. So when your process is right, your process is more important than your answer because your process is worth more marks than your answer. Your answer is only worth 1 mark. Okay, so I'm going to use the shade tool right now. So I'm going to exit full screen mode. So, sometimes a question like this, because it looks like a simple quotient rule question, students don't realize it involves chain rule. But if my u is equal to 2x minus 1 over x plus 2, then the outer function y is equal to u to the power of 6. So it is, in fact, chain rule question. So just like before, I'm going to move a little bit more quickly than the last one. I take the outer function, the derivative of the outer function first. That means bringing down the 6, taking my original rational equation, 2x minus 1 over x plus 2, and subtracting 1 from the exponent. So that's the derivative of the outside function. The derivative of the inside function is using quotient rule in detail to take the derivative of 2x minus 1 over x plus 2, not to the power of 6, just the inside function. So you can see in the last example, when I made a mistake in the plus or the mistake in the multiplication, it could throw off everything. So that's why, we're putting just 8 or 9 questions on the test and giving you sufficient time, because we want you to have time to go through these little minute details and these little steps. Okay, so to get to the next question, you notice that my derivative of u to the power of 6 has stayed the same, but I've essentially simplified this. So I probably should have included one more step there to really show the expansion of the numerator. This is just a question I wanted to go through quickly, and it's actually a try it yourself question so that you can see that you can repeat the same process that we did in that last example in order to get this type of answer. Notice again, 2x minus 1 to the power of 5 and x plus 2 to the power of 7 cannot be combined because they have nothing in common, no greatest common factor, nothing when you try to factor them that they have in common, and they are different bases, so we cannot subtract the base. You can only subtract the base when it's the same, and so then I have 6 times 5. that I combine to 30, and that's as far as I can go with this. But when we apply this to word problems, we will be able to go a bit further. I believe I have one more example that I want to just do as a practice, try it yourself, but I am going to kind of walk you through this a little bit because here we have higher order binomials, x squared plus 1 to the power of 3, 2 minus 3x to the power of 4. Why I'm including this in the example is please don't try to expand this. You are very likely to make lots of mistakes, and that's not what we're testing you on. So as a note, Mr. Bullock, maybe on the next test too, we should say use the power rule and the chain rule, because we are practicing the chain rule. So if the question is specifically saying use the power rule and the chain rule, and you try to expand this first, product rule and the chain rule, not the power rule, and you try to expand this so you can use the power rule, you will not be earning marks because the question is asking you to specifically use the product rule and the chain rule because that's what we need to see you exhibit, right? In university, not us, but in university, they're going to give you much higher powers, which is going to make it possible if you have 2 minus 3x to the power of 11. It's going to take you just an hour to try to expand that. So you need to use these rules that make life simpler and cut down on the possibility of any mistakes. Okay, so when I look at this, and in your notes, it'll appear in color in blue. This is the whole derivative of x squared plus 1 to the power of 3, incorporating the chain rule. And then we multiply that by the original second function, 2 minus 3x. I could call this one f of x, and this one g of x to make my life easier. So the original g of x, so then this part would be f prime of x. And this entire part would be g prime of x multiplied by my original f of x, whereas this is the original g of x. So you can see there's a product rule, but very clear that in the large expansion parts, we're applying the chain rule. Again, same thing. You want to really highlight where the greatest common factors are. So 2 minus 3x to the power of 4. Well, once you've expanded everything on the left-hand side and the right-hand side, you'll notice that there's a common 2 minus 3x to the power of something on both sides, but I'm going to take the power of 3 to be part of my greatest common factor. And there's an x squared plus 1 on both sides, but I'm going to take x squared plus 1 to the power of 2 to be part of the greatest common factor. And obviously 6x and negative 12 have a common 6 in common. The leftovers can go all in the second set of brackets, just like we did last time. And then we can simplify the second set of brackets. So the component over on this side, I would call my greatest common factor. The leftovers, you want to simplify the leftovers, but you also want to check if they're factorable. Like if this was a quadratic equation that could be factored, I would go further. This is not in this particular case. And here we're not expecting you to use the quadratic formula unless we were asking you in an application problem to look for a key point, or, you know, like we did last time, where the derivative is equal to 0. Here it is not factorable, so even though it's to the power of 2, a polynomial equation, we don't have to go further at that point. Okay, one last question. We just want to provide you with lots of practice, right? This is the same concept. It's not that we want to teach long lessons every day, but we want to provide you with lots of examples so that you are really understanding the concept. In regular Mary Ward, sometimes when we only have for a whole unit a 1-hour seminar, we give 3 examples, and then that's not enough, but there's lots of time at regular Mary Ward to do consultations individually with students. Here we don't have that, so we're trying to put our consultation questions in the actual lesson. So this is something that would probably come up with a question if we were all in the room consulting. I would definitely have students asking me more quotient rule questions. So again, we take the derivative of, notice this particular case though, there is no outside function. This is a straightforward quotient rule, except when I take the derivative of 2x plus 3 to the power of 7, I have the chain rule in the numerator. So the chain rule is not an outside function. Everything is not to the power of 4. The chain rule is individually for the numerator and the denominator. So this is why this particular question is different from the other quotient rule question. So you know what, I'm going to post this, and during our class time, I would like to give you the opportunity to look through this clearly. So if there's something you don't understand, this is an opportunity for you to consult and ask questions, but pretty straightforward because we have the derivative of the numerator, and then the chain rule comes again when I have to take the derivative of the denominator. But if that's something you don't understand, then that's a red flag that you want to talk to your teacher about. And when I post the PDF, there is going to be 2 slides on that to really show you detailed steps on how to solve it. Really for this test, kids, when you're doing your homework, and remember your homework, there is no set questions that Mr. Bullock and I expect you to do. Do as much practice as you would feel would prepare you for the test, right? That's why we're not making the unit work worth anything, because you know everyone is different. Some students need a lot of practice, some students need a little bit of practice, right? It's completely up to you what you do. That's just the questions that relate to these topics. However, where was I going with that? It kind of flew out of my head, but you might encounter questions like this as you're moving through textbook questions. There's also questions we haven't assigned in the textbook. You're welcome to do them, or you're welcome not to do them. We can always tell you and give you direction when you ask us something and we say that's way too difficult